Good day. In this learning module, we will tackle density, specific gravity, and specific volume. Methods of determining specific gravity of liquids and solids are discussed in this module. Specific volume, specific volume, which sometimes find its utility in pharmacy, is also described. Fundamental computations involving density, specific gravity, and specific volume are also covered. This module also introduces relevant calculations involving specific gravity of mixtures. At the end of this unit, the student will be able to 1. Define density, specific gravity, and specific volume, and determine each through appropriate calculations. 2. Calculate specific gravity from data derived from the use of a pyknometer. And third, apply specific gravity correctly in converting weight to volume and volume to weight. Now, as a review, remember that density is defined as the mass per unit volume of a substance. Therefore, its formula is equal to mass divided by the volume. While the density can be expressed in many different ways, density is usually expressed as grams per cubic centimeter. The United States Pharmacopoeia states that 1 milliliter may be used as the equivalent of 1 cubic centimeter because the density of water may be expressed as 1 gram per cc or 1 gram per ml. Other units may be used in expressing the density, such as gram per liter or even gram per cubic feet. Remember that the density is a concrete number, meaning to say it is a number that contains a denomination. And it is important to note that the denomination or the unit should always be stated when stating the numerical value of the density. As opposed to the density, specific gravity is a ratio expressed decimally of the weight of a substance to the weight of an equal volume of a substance chosen as a standard. Water is used as a standard for liquids and solids, and hydrogen is used as a standard for gases. Remember that both substances should be weighed at the same temperature, or the temperature of each should be known. Unlike density, specific gravity is an abstract number, meaning to say the specific gravity is unitless. While both specific gravity and density are physical constants, it is only specific gravity whose numerical value does not change at a specified temperature or at a specified condition. Remember that because of the varying ways to express the density or the varying units used to express the density, the numerical value of the density may vary for one substance taken at any different at any temperature or at any condition. Nevertheless, both specific gravity and density can be used to determine the identity of a substance or its purity. Both of these quantities are considered as physical constant. When we say a physical constant, we mean that by comparing the literature value from the one that we determine, we can assume that a particular substance is the same as the one in the literature when its density or its specific gravity is equal to the one that is stated in the literature. Now, most of the time, the specific gravity is determined using a picnometer, although some other methods may be used to determine the specific gravity as well. A the refractive index of the liquid can also be used to determine the specific gravity of substances, and a particular tube can also be used in determining specific gravity or density, and that is what we call the hydrometer. When using now, what is the importance? Now, what is the importance of density and specific gravity? Remember that for certain heterogeneous mixtures, meaning to say the two substances or the two or more substances which are mixed together do not combine homogeneously. You see phases in them. When in heterogeneous mixtures, when a particular substance has a density that is lower than the other, then it floats on top of the other substance. If it has a density or specific gravity that is greater than one substance, excuse me, when its density or specific gravity is greater than the other substance, then it simply settles at the bottom of the other substance. The lighter the density or specific gravity, or the smaller the density or specific gravity, the lighter is the substance, while the higher the density or the specific gravity, the heavier is the substance. As what you can see in this picture, oil most often have oils most often uh, oils most often have a specific gravity less than one, which is the specific gravity of water. So most oils float on top of water. You can also see in this table other substances whose specific gravities are less than one, and all of them are considered to be lighter than water. Included in this list is alcohol and many oils. Now, there are also substances whose specific gravities are greater than one, and these substances are said to be heavier than water. Water is known to have a specific gravity equal to 1, especially when its temperature is determined at 25 degrees Celsius. Most substances, most specific gravities of substances are determined at the standard temperature of 25 degrees Celsius, although other substances will require other temperatures. For example, the specific gravity of alcohol is determined at 15.56 degrees Celsius according to government regulations, and ether has a specific value or a specific gravity value determined at 20 degrees Celsius. We can see in this picture that chloroform having a specific gravity of 1.47 will settle at the bottom of water because it is heavier than it. This will be very important for you in your other subject, in particular in pharmaceutical inorganic chemistry and also in pharmaceutical organic chemistry, where you will be observing the color of the chloroform layer when a halogen is dissolved in it. So you will always find the chloroform layer at the bottom of the aqueous layer. Remember that its specific gravity is greater than 1. On the other hand, mineral oil, which is basically the component of your baby oil or rubbing oil, has a specific gravity less than 1, so it floats on top of water. Now, the presence of solutes in solutions will also increase the specific gravity of the solution, especially when the solute by itself has a specific gravity that is greater than 1. An example of this is the syrup. Syrup is a solution of sucrose in water because sucrose by itself has a specific gravity of greater than 1. Its solution in water will also have a specific gravity that is greater than 1. How important are density and specific gravity in in their clinical applications? So aside from those that are written in your learning module, we can also say that density and specific gravity are important in hematology or the study of the blood. Now, in order for us to get an idea on a person's hematocrit level or the amount of red blood cells, we need to centrifuge a whole blood, which is extracted from the patient. Now, because of the differences in the density and the specific gravity of the different components of blood, we can see layers forming after centrifugation. The plasma, which contains some proteins in the blood, including antibodies in the blood, will float on top of what we call the formed elements layer because the formed elements layer will contain the blood cells, such as your red blood cells, your white blood cells, and your platelets. Now, by looking at the amount of the formed elements, we can also diagnose or at least determine whether a person has a lower than normal hematocrit level or a higher than normal hematocrit level. Now, let us illustrate the first of the two methods of determining specific gravity. Remember that the specific gravity can be determined by two methods, one of which is called the pycnometer method. The other one is called the displacement method or the plummet method. A pycnometer is also known as the specific gravity bottle. A specific gravity bottle is similar to your volumetric flask, except that the specific gravity bottle does not have a long neck before the stopper. The pycnometer or specific gravity bottle has a ground glass stopper similar to your volumetric flask, but without the long neck, and the stopper also contains a capillary hole. The capillary hole will permit the release of the liquid that will be in excess in filling the pycnometer. Now, there can be a wide range of capacities or volumes of your pycnometer. So there is a pycnometer that has a capacity of 5 milliliters, 10 milliliters, sometimes 25, and others even have up to 50 milliliters. And you can find the capacity of the picnometer in the bottle itself. Now, what does that capacity mean? The volume that is stated in the bottle basically states that the bottle, once completely filled to the brim, will contain this volume. So, how do we perform the picnometer method? So, it's actually very simple. First is you determine the weight of the empty picnometer. The weight of the empty picnometer is basically your tare weight, which you will deduct from the weight of the filled picnometer. Next is you will determine the weight of pictometer that has been filled by the standard, which is distilled water. Now, how do you fill the picnometer? So you put sufficient amount of the substance until you form a concavity in the mouth of the picnometer. That is important to make sure that there will be no bubbles inside the picnometer. And then you will use the stopper, you will put it gently uh, in the mouth of the picnometer until the excess liquid pours out of the capillary hole of the bottle. Then you will wipe dry all the surface of the picnometer before you weigh it using the same balance where you weighed the empty picnometer. Take note that the field picnometer must not contain any bubbles because presence of bubbles will mean that the quantity is not the same as the stated volume of the picnometer. And then the third step is to weigh the picnometer, this time containing the substance of interest or the one that whose specific gravity you want to determine. Of course, you need to empty the picnometer first and let it dry before you fill it with a different substance. Let's take this problem as an example on how to determine the specific gravity. A, a 50 milliliter picnometer is found to weigh 120 grams when empty, 171 grams when filled with water, and 160 grams when filled with an unknown liquid. Calculate the specific gravity of the unknown liquid. Now remember that the specific gravity of any substance is defined as the ratio of the substance to I mean, the specific gravity of the substance is equal to the ratio of the weight of the substance to the weight of an equal volume of the standard, which is water for liquids. Now, how are we sure that the substance and the water have the same volume? Remember that in steps 2 and 3, you need to use the same picnometer for your standard and your substance. Having used the same picnometer, we are ensured that the volume of these two substances are the same. And take note that it was also highlighted that the picnometer should not contain any bubble to ensure the equality in the volume between the substance and the water. So, how do we get the weight of the substance? So, the weight of the substance is basically the weight of the pycnometer with the substance minus the weight of the pycnometer when it is empty. 160 grams minus 120 grams divided by the weight of an equal volume of water, which is basically the weight of pycnometer with water, 171 grams, minus the tare weight, which is 120 grams. And we will be able to get a specific gravity that is equal to 0.78. And because of the fact that the specific gravity is an abstract quantity, there is no unit in expressing the specific gravity. The grams will simply cancel out. The fact that the specific gravity is a ratio of two quantities with the same units, then the final answer will have no unit. Now, is it possible for us to determine the density of the unknown liquid, the density given in grams per milliliter? Yes, the density is the density has a symbol of d, or in physics, the Greek symbol or the Greek letter rho is used. The density is basically mass of the substance divided by its volume. Where are we going to get the mass of the substance? The mass of the substance is basically the weight of the pycnometer with the unknown liquid minus its tare weight, or the tare weight of the pycnometer, 120 grams, divided by the volume. Now, where are we going to get the volume? Because the pycnometer has a capacity of 50 milliliters, the volume of any substance placed in it will be the same. It will be 50 milliliters. So, we can now determine the density as equal to zero point 0.8 gram per ml. Take note that unlike specific gravity, density has a unit that is zero point 0.8 that is gram per ml. And if we will recall the specific gravity of the unknown substance, the numerical values of the density and the specific gravity are almost the same. So sometimes the specific gravity and the density are used interchangeably. Now, the other method of determining the specific gravity is called the plummet method or the displacement method. Now, this method of determining the specific gravity can be used in a wide variety of ways. This can be used in the determination of the specific gravity of liquids and also the specific gravity of solids. This method is based on Archimedes' principle, which states that a body immersed in a liquid displaces an amount of the liquid equal to its own volume and suffers an apparent loss in weight equal to the weight of the displaced liquid. So, what does it mean by that? So, it only means that when you put any substance in a tank containing a liquid, that substance will displace a volume of the liquid that is equal to its own volume. And the weight of the displaced liquid is the same as the apparent loss in weight in the substance that is immersed in it. Now, why is there a decrease in the weight of the substance that is immersed in a liquid? It is because of what we call the buoyant force that seems to go against the weight of the substance, which is defined by the force of gravity, G. It is for that reason that the Archimedes principle is also known as the law of buoyancy. Now, take note that for us to be able to successfully use the displacement method or the plummet method, the substance immersed in the liquid should be completely immersed in it. Later on, we will have an example where a substance may not be completely immersed in the liquid, and there is another way for us to determine the specific gravity of that substance. Now, remember that in the Archimedes principle, there are two things that you have to remember. First is that any substance immersed in the liquid will displace its own volume of liquid. And the second one is that that substance immersed in the liquid will suffer a decrease in weight that is equivalent to the weight of the displaced liquid. We will be using those two things in the Archimedes principle in calculating the specific gravity of the substance. Now, why do we need the plummet method? If you have watched the videos in the learning modules, you would have known the history of the Archimedes principle. Archimedes was an ancient philosopher and mathematician, and he was the first to use or to display the use of the buoyant force in determining um, the identity of substances. Now, for certain materials, it's easier for us to determine their volume. For example, for regular solids such as the sphere, the cylinder, the prism, and the cube, we will simply use the size or the length of their sides and or their radius or diameter in calculating their volumes. However, for certain solid substances which are irregularly shaped, it is much more difficult to determine their volume. But we can determine their volume by using Archimedes' principle, by placing irregularly shaped solids in liquids and taking note of the displacement in volume or the change in the volume of the liquid, we will be able to know the volume of the solid. It is basically the change in the volume of the liquid when the solid is placed or immersed in it. Now, the buoyant force or the decrease in the weight that is determined in the solid that is immersed in a liquid is the same as the weight of the displaced liquid. So those are the two things that you need to remember in the plummet method or the displacement method based on the Archimedes principle. Now, let's have this problem as an example illustrating the use of the displacement method in determining the specific gravity of liquids. In determining the specific gravity of liquids using the plummet method, we use a glass plummet. And the glass plummet is placed in both the standard, which is water, and the substance, which is, in this case, an oil. And then the we will be determining the apparent loss of weight of the glass plummet when immersed in both water and oil to determine the oil's specific gravity. Now we are ensured that the volume of the displaced liquid will be the same for both water and oil because the same glass plummet must be used in this method. Let me read the problem. A glass plummet weighs 12.64 grams in air, 8.57 grams when immersed in water, and 9.12 grams when immersed in an oil. Calculate the specific gravity of the oil. Remember again that the specific gravity is equal to the weight of the substance divided by the weight of an equal volume of water. Now, because we use the same plummet in both cases, let us suppose this rock represents our glass plummet. Okay? the because we are using the same glass plummet in both occasions, then we are sure that the volume displaced in water and the volume displaced in oil will have the same volume. So what we only need to do is to determine the weight of the displaced water and the weight of the displaced oil to represent the weight of an equal volume of water and the weight of the substance, respectively. So, where are we going to get those weights? We get them from the apparent loss in weight of the glass plummet. So, the apparent loss in weight of the glass plummet in oil is equal to 12.64 grams minus 9.12 grams, and the apparent loss in weight of the glass plummet in water is 12.64 grams minus 8.57 grams. So calculating these numerical values, we get an answer that is equal to 0.86. Take note that when the specific gravity is less than 1, it means to say that the substance is lighter than water, and most oils are lighter than water. So, is the oil heavier or lighter than water? We can say that the oil is indeed lighter than water. Now, we can also employ the plummet method or the displacement method in general in determining the specific gravity of solids. So this time we will not call the method the plummet method because we will not be using a glass plummet, but instead the solid itself is the one that we will immerse in the liquid, which is water. So in general, the method that is employed in determining the specific gravity of solids is called the displacement method based in the Archimedes principle. So we have several cases to consider here. We have to consider the apparent density of the solid, whether it floats in water or not, and its solubility in water. Because this time around, we will be immersing the solid in water to determine the solid's specific gravity. So the first case is for solids heavier than and insoluble in water. So for us to determine the specific gravity of these kinds of solids, we need to first divide the weight of the solid in air by the weight of water that it displaces when immersed in it. The weight of water displaced, or the apparent loss of weight in water, is equal to the weight of an equal volume of water. For example, if a piece of glass weighs 38.525 grams in air and 23.525 grams when immersed in water, what is its specific gravity? Okay, so let us first illustrate this problem. So we have a cylinder containing water, and we put in it a piece of glass. The piece of glass will displace its own volume of water according to Archimedes' principle. Now, we can get the apparent loss in weight of the solid to, to determine the weight of the displaced liquid. The weight of the displaced water is now the weight of an equal volume of water, which is the denominator in determining the specific gravity, which, as you might recall, is equal to the weight of the substance divided by the weight of an equal volume of water. So, by determining the weight of the displaced water by the solid, we are actually determining the weight of an equal volume of water. We know the weight of the substance in air, and that is 38.525 grams. The weight of the equal volume of water is the apparent loss in weight of the glass, and that is equal to 38.525 grams minus 23.525 grams. The denominator is actually equal to 15 grams. That's the weight of the displaced water. So we can just divide 38.525 grams by 15, and we get an answer that is equal to 2.57. And that is the specific gravity of the piece of glass. Now take note that the specific gravity is greater than 1, so we are sure that the piece of glass is indeed heavier than water. Now we can also use the displacement method in determining the specific gravity of solids heavier than but soluble in water. Now, why is this different? What makes this more complicated? Now, for this particular solid, we know that it is soluble in water. So it means to say that we cannot simply immerse the solid in water, otherwise, portions of it will become part of the solution. So, in order for us to determine the specific gravity of solids heavier than and soluble in water, we need to use a different liquid in which the solid is not soluble. An example of that liquid is an oil. Because of the difference in the polarity of water and oil, we are sure or partially sure that the solid will not be soluble in oil if it is soluble in water. Now, the important thing in determining the specific gravity of solids heavier than and soluble in water is that we need to note that the weights of equal volumes of any two substances are proportional to their specific gravities. To illustrate this, we can determine the specific gravity of this crystal of a chemical salt. A crystal of a chemical salt weighs 6.423 grams in air and 2.873 grams when immersed in an oil having a specific gravity of 0.858. What is the specific gravity of the oil? Now, what we can do here is we can determine the weight of the displaced oil, which is the same as the weight of an equal volume of oil. That will be equal to 6.423 grams, the weight of the chemical salt in air, minus 2.873 grams, the weight of the chemical soil when immersed in the oil. And this will be equal to 3.55 grams. Now, we know that the specific gravity of the oil is 0.858. We also know that this oil, at least in this particular experiment, has a weight of 3.55 grams. Now, the oil with a weight of 3.55 grams has the same volume as a chemical salt that weighs 6.423 grams. We can determine the specific gravity of the chemical salt using ratio and proportion. Take note that the numerator here represents the weights and the denominator here represents the specific gravity. Now, of course, you can interchange these two, but they should always be the same as the other side of the equation. So this should still be a weight and this should be a specific gravity. Another thing that you have to remember is that this portion of the equality refers to that of the oil, and this one is for the chemical salt. Another thing that you have to remember is that the weights should have the same volume. This weight of the chemical salt has the same volume as this um, weight of the oil because it is what we derive from Archimedes' principle. Rearranging the equality, we get the value for the x. So the x is equal to 0.858 times 6.423 grams divided by 3.55 grams. And we get an answer that is equal to 1.55. That is now the specific gravity of the salt. Now, if you would like a different method to determine the specific gravity of the chemical salt, there is another way. Remember, in the previous slide, we mentioned that weights of the substances are of the same volume are proportional to their specific gravities. So, knowing the weight of an equal volume of oil or the weight of the displaced oil, we can actually determine the weight of the displaced water if the chemical salt were to be immersed in water. But that is not possible because we know that the chemical salt will be soluble in water. Okay, so it's just an assumption. And that is also the weight of an equal volume of water, which is the standard that we use in determining the specific gravity in this particular formula. The specific gravity, remember, is the weight of the substance divided by the weight of an equal volume of water. So to be able to use this formula, we need to get the weight of an equal volume of water. And how do we get that? We know that the specific gravity of water is 1. We also know that the specific gravity of the oil is equal to 0.858. Now, we also know that the chemical crystal salt displaces a volume of the oil that weighs 3.55 grams. Therefore, we can determine the amount of water with the same volume that could have been displaced by the same volume of the chemical salt using this proportionality. So once again, in the numerator, we have the weights. They have the same volume. And in the denominator, we have the specific gravities um, of these substances. This one is for water, and this one is for the oil. So 3.55 divided by 0.858 is equal to 4.1375 grams. That's the weight of the displaced water if the crystal were placed in it. Now we can use this formula. We know that the crystal salt weighs 6.423 grams in air, and the weight of the displaced water is equal to 4.1375 grams. The answer should be the same, 1.55, the specific gravity of the salt. Now, what are we going to do if the solid is lighter than and insoluble in water? Once again, remember what we mentioned before in the Archimedes principle. The solid should be completely immersed in a particular liquid for the solid to displace its own volume of the liquid. And it is only when the solid is immersed completely in the liquid that the apparent loss in weight of the solid will be the same as the weight of the displaced liquid. Now, what happens when the solid is lighter than water? So, what happens is that the object will obviously float and it will only displace a volume of the liquid that is equal to the immersed portion of it. So, the volume that we get here, the volume of the liquid, will not be the same as the volume of the solid that floats in the liquid. It is only equal to a fraction of it. So the Archimedes principle appears to not be applicable in this case. But there is a way for us to be able to use the displacement method in determining the specific gravity of solids lighter than and insoluble in water. And that involves the use of a sinker. The sinker will be attached to the solid to prevent it from floating, and it will have no apparent weight at all because we need to know the weight of the sinker when it is immersed in the liquid. So we will be subtracting that weight of the sinker when immersed in the water. So remember that the weight of the sinker when immersed in water must be known so that the combined weight of the solid in air and the sinker in water may be calculated. By subtracting from this weight of solid and sinker when immersed in water, the weight of the water displaced by the solid is calculated. So what do we mean by these statements? It is better for us to use this example to explain how to determine the specific gravity of solids lighter than water but insoluble in it. So let's take, for example, a piece of wax. Waxes are commonly known to be lighter than water. They float in water. A piece of wax weighs 16.35 grams in air, and a sinker weighs 32.84 grams when immersed in water. When they are fastened together and immersed in the water, their combined weight is 29.68 grams. Calculate the specific gravity of the wax. So once again, our formula for specific gravity is equal to the weight of the substance, which is the wax, divided by the weight of the displaced liquid or the weight of an equal volume of water. Or basically, it is the weight of the displaced water with the same volume as the wax. But of course, that is not possible for us to directly determine because the wax floats in water. So, how do we now determine the apparent weight loss of wax in water? So, take note that we know the weight of the wax in air, 16.35 grams. We also know the weight of the sinker in water. So we just add it here, 32.84 grams. And then we also know the combined weight of the wax and the sinker in water. So we will subtract that value, 29.68 grams, from this sum. Okay? Why is that so? Remember that this is the weight of the wax in air. And this is the weight of the sinker in water. Now, 29.68 grams is the weight of both wax and sinker in water. Now, of course, we cannot directly determine the weight of wax in water because simply wax will float in water. And it will be erroneous to determine the weight that it displaces. So we put together with it, no, a sinker which will um, pull down the wax and allow it to be immersed in water. Now the combined weight of the wax in water, of the wax and the sinker in water, will therefore be um, wax in water and sinker in water. So basically, this value, 29.68, refers to the weight of the wax in water if it were completely immersed in it, and the sinker, the weight of the sinker in water, which obviously will be heavier than water, so it will sink in the water. And so by subtracting this amount from this sum, we are actually taking out the effect of the sinker that is fastened together with the wax. So we will now be able to get the weight of the displaced water that is only due to the wax. And that is equal to 19.51 grams. This is the weight of the water that is only due to that volume of wax that is completely immersed in it because we subtracted already the weight of the sinker in water. So we can now determine the specific gravity of the wax. So the weight of the wax is 16.35 grams, And the weight of an equal volume of water, or the apparent weight loss of wax in water, is 19.51 grams. The specific gravity is therefore equal to 0.84, which is less than 1. So the wax is definitely lighter than water. Now, sometimes we may need to determine the specific gravity of granulated solids. Now, for granulated solids which are heavier than and insoluble in water, we will be using a specific gravity bottle, which we call the pycnometer, or a volumetric flask. Now, remember that the volume of crystals, powders, and other forms of solids cannot be directly measured. So, if such a substance is insoluble in water, we may weigh a portion of it, introduce this amount into the bottle, fill up the bottle with water, and weigh the mixture. The solid will displace a volume of water equal to its own volume, and the weight of the displaced water may be or can be calculated. Let's take this problem as an example. A bottle weighs 50 grams when empty and 96.8 grams when filled with water. If 28.8 grams of granulated metal are placed in the bottle and the bottle is filled with water, the total weight is 118.4 grams. What is the specific gravity of the metal? So in this case, we don't know the volume of the granulated metal. Now remember that the metal displaces its own volume. Okay? Now, by getting the difference in the weight of water that fills the specific gravity bottle and the metal, okay? So by getting the sum of the weights of the water used to fill a specific gravity bottle and the weight of the metal and the weight of the water and the metal contained in a specific gravity bottle, we will be able to determine the weight of the water that is displaced by the metal. And that information is important for us to determine the specific gravity. Okay, so once again, the specific gravity is equal to the weight of the substance divided by the weight of the water that it displaces. So, first, we need to determine the weight of water that fills the bottle. And we can get that by subtracting 50 grams, which is the tare weight of the bottle, from 96.8 grams, the weight of the bottle when filled with water. And this is equal to 46.8 grams. This is the weight of water that fills the bottle. Next, we can determine the combined weight of water and the metal by simply getting the sum of 46.8 grams and the weight of the granulated metal, which is 28.8 grams, and that is 75.6 grams. This is the combined weight of water and the metal. Next is we know that when the granulated metal and water are placed in the bottle, the weight is 118.4. So 118.4 grams minus 50 grams will give us the combined weight of water and metal in the bottle. Now, what do you notice? You will notice that the combined weight of water and metal is greater than that of the combined weight of water and metal in the bottle. Why is that so? Remember that we determined the combined weight of water and the metal by simply adding the weight of the water that is contained in the bottle and the weight of the metal. Now, when the metal is placed in the bottle and the rest of the volume of the bottle is filled with water, the metal will displace a certain volume. So that volume is supposed to be equal to the volume of the water that should have been there if the water were the only one present in the bottle. So, by getting the difference between these two, 75.6 grams minus 68.4 grams, we will be able to determine the weight of the water displaced by the metal. And that weight of water displaced by the metal is basically the weight of an equal volume of the granulated metal. So we can now use our formula for specific gravity in determining the specific gravity of the granulated metal. And that will be equal to 28.8 grams divided by 7.2 grams. And this is equal to 4 or 4.0, which is greater than 1. So we know that the granulated metal is heavier than water. Now we have this terminology that is known as the specific volume. The specific volume is a ratio that is expressed decimally of the volume of the substance to the volume of an equal weight of another substance. Now we have another terminology or another quantity that is known as the specific volume. The specific volume is the ratio expressed decimally of the volume of a substance to the volume of an equal weight of another substance, taken as a standard. Same as with specific gravity, water is used for both solids and liquids, both having the same temperature. The formula for the specific volume is equal to the volume of the substance divided by the volume of an equal weight of water. Now remember that because specific volume refers now to the volume of the substance and the volume of an equal weight of water, basically specific volume is the inverse quantity of a specific gravity. So we can determine the specific volume if we know the specific gravity of any substance. The same methods apply. Now we can use the specific gravity in determining the weight or the volume of a liquid with known volume or weight respectively and their specific gravities. Given over here are the formulas that we can use to determine the weight and the volume of liquids or even solids. Let's have these examples to illustrate how we will be able to use the specific gravity or the specific volume in determining the weight or the volume of the substance. So first, what is the weight of 60 milliliters of peppermint oil having a specific gravity of zero point 0.9? Is this substance lighter or heavier than water? Now let us first answer the second question. Is this substance lighter or heavier than water? Because the specific gravity is less than 1, we can say that the substance is lighter than water. Now what we have here is a volume. Now, what I normally do is that I just think that a specific gravity is approximately equal to the density of a substance. Remember that the only difference between these two is that the specific gravity is unitless and it is an abstract quantity, meaning to say its numerical value will not change no matter what at any given condition. Now, the density is a quantity with a unit. The unit varies, so the numerical value may also vary. But the unit for the density is always mass unit per volume unit. For example, the unit can be grams per ml. Now, remember that 1 milliliter of water has a weight of 1 gram. So, if the density is given in grams per ml, it is basically the same as the numerical value of its specific gravity because specific gravity is defined as the weight of the substance divided by the weight of an equal volume of water. So if the volume of substance is given in its density, we can convert it to the weight of an equal volume of water. So when the density has a unit that is grams per ml, the numerical value of density is the same or similar to specific gravity because of this equality where 1 ml of water has a weight of 1 gram. So there is an imaginary unit that I always remember for specific gravity, and that is grams per ml. So to determine the weight of 60 milliliters of water, what I do is I multiply it by zero point 0.9. So 60 milliliters times zero point 0.9 is equal to 54 grams. Okay? And because of the imaginary, again, this is not real unit. Because of the imaginary unit of the specific gravity that is grams per ml, I cancel the ml. So the unit that I get is grams. Another example is this. What is the weight in grams of 1 fluid ounce of clove oil with a specific gravity of 1.04? Now remember that the imaginary unit of the specific gravity is gram per ml. Okay? So we need to convert the fluid ounce to milliliters to be able to get the equivalent weight of clove oil in grams. One fluid ounce is equal to 29.57 milliliters. So 29.57 milliliters times the specific gravity, which is 1.04, equals 30.7528 grams, or approximately equal to 30.8 grams. Okay? Remember also that in our discussion of significant figures and rounding off, in multiplying and dividing numerical values, the product or the quotient should have um, as little significant figures as the number with the least number of significant figures. So we can approximate this quantity to this quantity, which is 30.8 grams, having three significant figures. And lastly, we have this problem. What is the volume in milliliters of 100 grams of glacial acetic acid with a specific gravity of 1.05? 1.05. Okay, remember again that the weight of a substance is equal to its volume times its specific gravity. Therefore, we can determine the volume of any substance as the weight divided by a specific gravity. Now, remember again that if the unit of the weight is in grams, our specific gravity has an imaginary unit of gram per ml. So we cancel the gram, so the unit of our volume will be in milliliters. So the volume in milliliters of 100 grams of glacial acetic acid will be equal to this expression, 100 grams divided by 1.05, and that will be equal to 95.24 milliliters. Again, employing what we know um, about the significant figures, and we should only express our answer with one significant figure, but it seems to be very difficult in this case, so we'll just keep this answer at the moment. 95.24 ml, or about 95 milliliters. And that ends our discussion of density, specific gravity, and specific volume.